All right. Welcome, everyone. This is my presentation on Fleet, the Edge conference. Let's get into it. Yeah, a couple things. I'm going to do this in like one take. I don't like to do any editing or anything, so I might make mistakes. Also, since I kind of know this is recorded and it's going to be distributed and everything, this talk will probably be pretty dense, like a lot of information, and I might speak a little fast, but hopefully you can just go back to different sections. I'm going to try to cover a lot because I really want to, for this conference, get into a lot of the more technical details, not a lot of the kind of high level things. Like you get into a lot of the things specific to Edge. So specifically about me, so I'm Darren Shepard, co-founder or CTO and co-founder of Rancher Labs. I created Fleet and K3S just so you kind of understand where I'm coming from. From creating K3S, have been fooling around a lot in this kind of edge space with Kubernetes, and I very much care about building simple things. You can follow me on Twitter at I build the cloud. Yeah. Okay. Enough about me. So moving in. So I want to talk about Fleet. So Fleet is basically kind of the tagline for it is GitOps at scale. So it's suitable from 1 to 1 million clusters. We have honestly tested it to 1 million clusters. I just concluded the testing of that. I went it went better than I thought. I wouldn't recommend anyone run 1 million clusters right now, but the architecture is definitely capable of it. And we have a couple more things to make it rock solid to, smooth that out. I'll talk about some of that later. But basically, Fleet is GitOps at scale. So the scale part is really the important part of Fleet. And generally, what are you going to do with Fleet? It's pretty much you're going to manage everything. So this includes like policy, anything that's Kubernetes related. So basically, policy. So how what's the security components or RBAC or whatnot. Anything application deployments can go through this, and then also infrastructure maintenance, because what we're finding is basically anything can be described as a Kubernetes manifest. And because of that, you can then use Kubernetes controllers and approaches or GitOps or not to also control your infrastructure. So you can use this also to control the maintenance. And when you're talking about edge devices, the models and stuff we're looking at is actually managing like OS rollouts and updates through Kubernetes. So Fleet also, once it deploys things, it monitors the resources live, so you can get back status of whether or not things are in sync and if they're ready. So 2 very basic checks, but quite powerful to get an overall status of your deployment across all your devices. And the key point about Fleet in terms of the architecture is that there is a centralized component. This gives us visibility from kind of one place where you can get a visibility of everything under management. You can control who has access to that central place. So you can say who's allowed to deploy to what clusters and what accounts are they be able to use to deploy software there. And also this gives us the ability to do controlled rollouts. So I'll talk about that a lot more in detail later. Okay, so just at a high level, but in this talk, what I specifically want to get to is like Fleet is, we market it as GitOps at scale, and Git's not actually really the most interesting thing about Fleet. It's really more about the engine of how we accomplished what we've done. Because when Fleet really came about as K3S grew in popularity, the next obvious thing was people are like, well, I've deployed K3S in all these different places. How do I then manage that? I need some, and that's where Fleet came from. And then as we began to build this up, it's like, oh, GitOps perfectly matches the model I'd want to use to deploy things. So, we brought in Git. So at this Edge conference, I hope I don't really need to say why millions. We're looking at Edge, these things, basically anywhere Linux is being deployed today, people are looking at running Kubernetes on it. So there's this idea of how do we manage things and edge deployment? Do we treat it as one big cluster and each device is a node? Or do we say like each device is a cluster and so we have a lot of little clusters? What we've seen in practice is the model of a lot of smaller clusters becomes a lot easier to manage because it becomes more of a configuration management problem. So that's the architecture more that Fleet goes towards, is the idea of a lot of little clusters. And then just how do you manage the configuration of them? So this is not a abstraction or federation type problem. This is what we look at as largely a configuration management problem. So getting into the architecture of Fleet. So internally, Fleet has this concept of bundles. And this becomes really important because, as I said, Git's not the it's not kind of like the core, I guess the core value of Fleet, even though we market it as like a GitOps solution. Really, it's about the engine under the hood. And so we have this concept of bundles. So anything that's deployed from Git turns into a bundle. And then we basically map the bundles to where they want to be deployed, like different clusters. You can group clusters. Those are the cluster groups. And then the agents will deploy those. So from a high level concepts, we kind of have bundles or Git repos. Like Git repos will produce a bundle. So it's like bundles mapping to clusters and cluster groups. Everything in Fleet is done in like a pure Kubernetes way. There's no proprietary API formats or anything. Everything's exposed as a Kubernetes API using Kubernetes controllers. And this was really important about the scalability of this, because the scaling of Fleet actually meant we had to scale Kubernetes itself. And I'll talk about that a little bit later. So there's fundamentally two components to Fleet. There's the Fleet controller / manager. I kind of use those two terms interchangeably. But that runs on a centralized Kubernetes cluster. That is the place where you're going to communicate to Git if you're, for a GitOps model. And this works in a two-stage pull model. So first, we pull state from Git. We then determine where those resources need to be deployed to. And then the Fleet agents will then pull from the manager down. So everything's pull, and it's like 2 stages. So besides the central controller manager, we also have the Fleet agents. So there's 1 agent per cluster. The agent is what actually does the deployment. It effectively gets its desired state from the Fleet manager. It deploys the resources, and it does that using Helm. That does not mean you need to use Helm to use Fleet. It's just whatever input you give into the system. If it's either, right now we support either raw Kubernetes manifests, Helm charts, or customize, whichever one of those approaches you use, the output artifact is going to be a Helm chart, and that's what's actually installed into the cluster. And there's a lot of reasons why we use the Helm chart, and I'll talk about that a little bit later. But so once the agent deploys the Helm chart, it will then watch the resources for what I mentioned before, the 2 basic things of, is it ready, and then has it been modified? So anything that was changed after the fact will pop up, and Fleet will identify that. So the entire idea of this is you store all your desired state, and then how that state or application should be mapped to all the downstream clusters. And then Fleet just kind of takes care of it and ensures that the system is sane. So just kind of some random points about Fleet. This is what I mentioned before. It's like Git is really the least interesting part of Fleet. In fact, when we first built Fleet, we had no Git integration because we're like, well, we can just hook it up to Argo or Flux. We realized that was just adding a lot more complexity for for the users. It was simple enough to just plug into Git directly, but Fleet can still actually plug into an existing pipeline. So if you have like Argo, Flux, Spinnaker, any other pipeline that's like deploying Kubernetes things, you can very easily plug Fleet into that, because what Fleet literally does is, like, on git commit, we just run Fleet apply. Like, there's a command line kind of running behind the scenes where we just take the Git repo and then type, we run it, but you run Fleet apply, that generates a manifest resource, and then that gets applied to Kubernetes. So you can plug this into an existing workflow where you just say, okay, we'll run Fleet apply, but don't apply it to Kubernetes, just save the output, and then use your existing pipeline to then deploy that output to the Fleet manager, and then the Fleet manager will then deploy it out to all the clusters. But anyway, so Git's kind of the least interesting thing here. The power of Fleet and the most effort we put into is actually like the management engine tracking the bundles and mapping them to clusters and how that communicates to the agents, how to make that scale to 1 million. Basically, when you remove Git from Fleet, you realize Fleet becomes effectively just a massively scalable multi-cluster manager. And Rancher, the company I co-founded and work for, is that's what we've been doing the last 6 years. We've been doing multi-cluster management. We've kind of pioneered that space. And so a lot of the learnings of how to scale these systems has gone into Fleet. And so this is why, sorry, I was just checking something, but this is why Fleet is actually really important for the future of Rancher, our multi-cluster manager, because it is going to become the heart of it. And I'll talk a little bit about that later too. Okay, so just some comparisons to projects already out there. So the obvious ones, I probably should have put KubeEdge in there. I'll mention it slightly. But because Fleet is marketed as like GitOps, so immediately Argo and Flux, both of these are great projects. The architectures of them just didn't really align with what we needed. So Argo is conceptually appears very similar to Fleet because it's a central thing. You can define clusters, you can do multi-cluster deployments through Argo. But fundamentally, Argo is a push engine, a push architecture, and it has its own custom deployment engine. Like it deploys resources and tracks them itself. And I'll explain why that's important when I get down to the Fleet section. So Flux is also great. I really like the simplicity Flux. A lot of people are very successful with running Flux. It's a very simple pull model where you run something in the cluster and that talks to Git. It clones the resources and it deploys. The downsides of this model is just that there's no central control beyond Git. And a lot of people have gone very far with creating branching strategies and different rollouts and whatnot. But at the end of the day, it's very hard to programmatically interact with Git. And it also becomes a scaling problem because you're talking about scaling Git clones and Git check-ins. This was something we saw firsthand with Rancher. Our Rancher product will check these Git repos in order to pull down manifests for Helm. This is not related to GitOps, but it checks Git repos. And just if you just do something naive, like just do a poll in a loop, that takes a lot of bandwidth. And so it's like you have to actually get a little tricky of how you want to scale just a lot of things checking Git. So Fleet, the way it's different from these two is Fleet uses a two-stage poll architecture. So like the Flux model is fairly scalable, except for the fact they're all hitting Git, and so you have to worry about kind of scaling your Git service. But Fleet uses a two-stage poll architecture, and we've proven this already to 1 million clusters, whatever. It's massively scalable. It's much easier to scale a poll model. We use Helm as the deployment engine, and the reason why we do this is it's kind of Helm has already figured out a lot of these things of, it's like I have a desired state, which is a set of YAML, and I want to apply it. So I need to compare it to what's already there. So that means like I need to either create, update, or delete resources. And then after I've done that, I also need to save a manifest of what I did. So I know the next time coming around, or an inventory, the next time I come around, I know how to update those resources. What it should have been versus what's actually there, and kind of do a three-way diff and whatnot. So Helm has basically already figured that all out. So we didn't really want to write our own engine because we actually started that way of like, oh, let's just write our own engine. And we realized, oh, this overlaps a lot with Helm. We might as just use Helm. And a lot of the issues people have with Helm, if you have like an opinion about it, has much more to do with the templating or authoring Helm charts, which is irrelevant here because we're actually programmatically interacting with Helm. We're dynamically creating charts and then using Helm to deploy things. So whatever opinions you have about using Helm doesn't really apply here because you don't have to use it, but it's actually, in fact, a really nice way to track resources. So once I get onto the cluster, I can just do something like Helm ls, and I can see here's everything that's installed. Everything's defined as a Helm release, and then I can look in the releases and look at the manifests, and then that'll also show me here's all the resources that should be in there. So it's very easy to audit a a cluster at that point. It's very similar to like when you install an RPM package, or Debian is one I actually know a little better, is like when you install the Debian packages, you get like the SHA files. We had lists like, here's all the files that should be on your system. Here's all the hashes or the digests. And so you can then check it. You can write some script to them. So it's very similar. Helm does a similar thing for me. So the last point is one that's like super important for when I say like Fleet is a lot more than just Git, because we layered Git on top of this concept of bundles, is I can programmatically interact with bundles if I want to. And this is where, like, for us, Rancher, we're doing multi-cluster management. Fleet is going to become the core engine of everything that we're doing in Rancher, because we can just basically dynamically create bundles, hand that to Fleet, and then Fleet can go and distribute that everywhere. So the Git flow is much nicer for humans, but it's very difficult to interact with programmatically or script or automate. And there's a lot of things. So if I'm actually writing a program and I want to plug into this flow, it makes more sense to go with this bundle layer. So I have that kind of layer right below Git with Fleet. So I want to talk about the pull versus push, because they're saying, well, Argo is very similar, but it was a push model, and that fundamentally, kind of disqualified it from the scaling requirements we need. So push in general is very hard to scale. So Rancher 2 right now, the current architecture, like when we created Rancher 2, was actually a push model. We had a set of centralized controllers, which would then communicate out to all the clusters that it has under management, and it would push data out. It would decide who need to be updated, what's the state. So Rancher 2 right now scales to thousands of clusters. Like, it's fairly scalable. It's more scalable than most of the enterprise needs right now. When as soon as I go to Edge, there's two problems with it. I can't get to like 1 million very easily. Like, it would be significantly difficult. Also, it's way too chatty. So we've really had, with the experience we've done with Rancher, firsthand experience with the complexities of a push model and how far we can go with that. So when people talk about push versus pull in terms of the scalability, it's not really about the data. It's not about if I push data or if I pull data. Conceptually, if it was just about moving data, that's very simple. Like, you could scale both either way. So it's not about moving data. It's actually, when you say push versus pull, it's about where are the brains of the operation? Who has the logic to do the thing you want to do? So in a pull model, you typically put all the brains, you push it out towards the edge. So when you do that, what happens is when you try to actually do an operation, typically there's a lot of like CPU or communication or steps you need to do to actually perform an operation. But if you move kind of the brains out, then all you have to do is just tell it its desired state, and then it can figure out what it needs to do. It's kind of logically like the idea of like, well, if the desired state is like, I want to move my hand, it's like, you tell your brain like, oh, I want to move my hand up. Then your brain figures out like all these things. It's communicating all the muscles and nerves, and it's doing all those things. So the problem with in the push model is you have a tendency to write all your code is like kind of the brains of the operation are all centralized, and then it becomes very chatty because you need to communicate to the downstream device, figure out what the current state is, diff it. All these things are happening during deployment. So if you're doing that centralized, it just won't scale. And then it's also like, I'm trying to deploy some software and it fails halfway through. Like, well, what happens then? Like, you're in the middle. And so it becomes more brittle. But by basically pushing everything out to like kind of moving the brains of the operation all the way out to the edge, you can just give it a small piece of information, which is basically its desired state. So it's like, here's 1 kilobyte of information. You go and do that, and it executes everything. So, and in practice, as we test this, this has worked out. This is nothing, we invented. This is well known kind of within distributed systems. So I want to go into detail specifically, how does Fleet deploy from Git? So this we'll see like how I'll talk about kind of the different layers here. So like, first, the manager detects there's a Git commit, and then it clones. When we clone the Git, we then run Fleet apply from the Git source. So Fleet apply is basically just going to read the directory of all the resources and then create a bundle resource in Fleet. So this is the point where it's like if you didn't want to do Git and you wanted to just programmatically interact with the system, you just wouldn't do the Git and Fleet apply. Well, you kind of start at Fleet apply. You can just basically create bundles yourself. It's an API, it's documented or whatever. You can create bundles and then deploy those. But so when Git runs, we run Fleet apply, creates a bundle. That whole operation of like reading the Git stuff and running Fleet apply is done in a Kubernetes job. So it's done in a pod. It's like secure and isolated, and it's in a dedicated service account. So this was kind of important to us because we've ran into other security issues with Rancher today, where we're cloning Git repos and then kind of running Helm against those and everything. And we had to put all this jailing and stuff, to make sure that was actually secure. So this model was very nice to be able to just launch a pod that runs the operation, does it all secure. We're actually leveraging some Tekton bits here, some pieces of code from Tekton. And that was also why it was really easy to add Git support to Fleet, was because we leveraged some stuff from Tekton, and the whole process is fairly simple. But once you have so now once I have this bundle defined in Fleet, the manager or controller will then figure out what are the target clusters that need to deploy. What are the target clusters that the bundle needs to be deployed to? So it will then go and create a bundle deployment resource, one of those per target cluster. And the bundle deployment is a very small resource. It contains a content hash and then deployment options. So the deployment options might be like Helm values or timeout values. They're like just a couple flags that aren't directly tied to the content, because we take all the content from Git and then we kind of hash that and we store that. It's actually stored in Kubernetes. It shouldn't be a lot of content. But it's all stored in there. But so the bundle deployment just has a hash and some options. So it's a very small resource. So now the agent has a standard Kubernetes watch that goes back to the Fleet manager. So it will watch bundle deployments, and the bundle deployments are put into a dedicated namespace for that cluster. So every single cluster is a namespace is created for it, and the agent has a service account that can only list bundle deployments in that namespace. So it sits there and it watches them. So if there's a new one, it will see it. Then it will look at the bundle deployment. If that hasn't been deployed, then it will take the content hash and it will download the content from the Fleet manager. There's a separate resource called content in the Fleet API group. So it'll download the content. It will on the fly create a Helm chart. I could do a whole talk on just how we manage the Helm charts and the resources and how we configure the resources. There's a lot of power. Refer to the documentation. I can't cover it in this talk, but we generate the Helm chart and then basically we run Helm to deploy. Once we have Helm deployed, once we have it, created the chart and deployed it, we then update back the status for the bundle. And then after that, the agent will start live monitoring the resources. And as the monitoring, like as something changes, if a resource is not ready or it's been modified or it's been deleted, something like that, we'll then try to post back up to the centralized Fleet manager the status. So in general, if you look at the agent, like how does this scale, how do we get this scale really far, is like we've taken extra care of, like, even though we're using a standard Kubernetes architecture and controllers, we make sure that the agent communication is optimized, that all we do is we list and watch bundle deployments, and those are small resources. So it's not a lot of data going over the wire. Then we update bundle deployments to say that they succeeded or they're ready, like whatever the status is. And then on some interval, we will update the cluster status if we can. And the cluster status is just basically saying like how many ready nodes are there, and just to check in, just to know that like, hey, I last saw my agent, 2 hours ago. Because the next bullet here is like the agent is not required to be running. So Fleet can go, like Fleet, the central manager, is basically just updating all this desired state. And when the agents can operate, they will pull down the state and then post back the status. So the agents don't need to be running. So agents on these downstream clusters, they can just be ran during like a certain window. Like, if you're doing some retail, setup or something like that, you want to update at night, then you can create a very simple kind of like cron in Kubernetes to basically scale the agent to 0 and then scale it to 1, during the maintenance window. And then so it'll check in and it'll try to download its status. Also, if it doesn't have a connection, like you just have a bad internet connection or it goes down, the standard Kubernetes architecture or whatever, or our libraries all in client Go, will just pick up where it last left off. It will reconnect when it can. It will refresh its state, and it will sync back up. So it's eventually consistent here. And that's also an important part of scaling this system, is that we're not assuming that, like I say, like, oh, I deploy, like I want to do a deployment to 10,000 clusters. We're not assuming that's going to happen like in a second. This is an eventually consistent system. Most likely people are going to roll out over a larger period and want to ensure that, do buckets of deployments at a time. And there's a bunch of fancy rollout strategies that you can do in Fleet. And again, I don't have time to go through all those details, but that's one of the things that Fleet will do is partition the target clusters and, like, do one partition or do multiple partitions. You can say how many failing partitions you have before you move forward. And anyways, you can configure however you want. Okay. Oops. My last slide went by. Oh, okay. Yeah. So in general, so that just about that sums up kind of Fleet. That was the last slide. That was the last slide. So so just in summary, so Fleet right now it is basically pitched as GitOps at scale, and it's for the specific GitOps operations and whatnot. I thought I had more. No. Okay, I have more slides. Okay, sorry about that. See, I told you I'll mess up on this. Okay, yeah, okay. From current slide. There we go. Okay, so I want other things I want to point out about Fleet. It's written purely as Kubernetes controllers. So both the manager and the agent are written as controllers. So this was really important because we didn't want to introduce a lot of new components. It's like how to manage. It's like Kubernetes already can manage state. It already has a API structure and standard. It's like any new architectural layer seemed more complicated. So we wanted to create like what was the simplest thing. So we actually were seeing if we can just scale the existing Kubernetes architecture, because it's well known, and it's easier to scale it, and it would be better than me just trying to come up with some brand new thing. And basically we proved that we can scale it. The one thing is we just have to take extra care when it came to the communication from the agent to the manager. So that communication path, we're very careful about the size of the resources, how many times we make calls, but everything else is just written as a standard controller. No real fanciness considered in terms of how to scale it. So in order to scale a controller architecture to millions of objects, the first thing is you have to use Kind. Kind is a project that came out of K3S, which is you can run any Kubernetes cluster on a relational database like MySQL, RDS, Postgres. So for our scaling test, we ran things on RDS instances, like basically the largest ones we could get. They were like 384 gigabytes of RAM. Honestly, we didn't really push them very hard. In general, when you get into these really high scaling things, the bottleneck is almost always Kubernetes, not the database if you're running against like MySQL. But etcd just fundamentally can't support this scale. Like they have a key space that I think is theoretically limited to like 8 gigabytes, but typically it's like 5 gigabytes. So you can really only have about like 5 gigabytes of data in etcd. And we well exceed that when we get up to like 1 million clusters. So like, yeah, you can have hundreds of gigabytes of data in Kind, and it should still work. But the one downside is controller restarts are quite slow, because the way controllers are written in general is this is how kind of the architecture works. Is you have to cache all the data in memory. Even if you don't cache, you have to do a full scan at some point. So you're going to have to pull down all of the data at some point. And because of that, it's slow to grab all that data. So the biggest problem we have with scaling to that far is like if we have to reset the whole system, like take it down and bring it back up, it could take over an hour to rebuild those caches, which stinks. So you have to be very careful about how you roll out updates and stuff, because you don't want to bring down your system that long. So you want to make sure you have like one running, and then you build up the caches on the other and stuff like that. So there's things we're actually trying to work on optimizations there to help there. But also oops, that's my timer. I hit 30 minutes. So the security model is built around service accounts in Kubernetes. So Fleet is dynamically creating and issuing accounts for clusters. I think a lot of this is documented it's in the documentation, but yeah, I mean, I can't cover it in detail how the security is managed, but every single cluster has its own unique identity, and it's locked down to only seeing bundle deployments for that cluster. So just the project status roadmap, where we're going right now, we're basically stabilizing. You know, we put out, I think I had tweeted and said it. Well, anyways, by the time, no, sorry. So we should have what's, I think, officially declared as like a stable release by the end of this month, but it's kind of already out there, and it's kind of, I guess, release candidate. I don't know what you say, but it's stable. It's stabilizing this month, and so the plan is by the end of October to call it stable. Okay, so it's installable as basically its own component. You can install Fleet. There's like it's like just a standard Kubernetes controller. So you just basically install it as a Helm chart. Has no tie-in to any other Rancher project. That's going to be maintained separately from any other Rancher project. Ideally, I would really, if this takes off and people like it and use it, I would love to see this go to CNCF. But it is very heavily integrated into Rancher 2.5 right now, and going forward, pretty much all of Rancher is going to be built on top of Fleet. So, even if there wasn't massive community adoption of Fleet by itself, it's still extremely important component for Rancher in general. So you can find all the source code in GitHub, and then also the docs are available at that URL, fleet.rancher.io. And thank you for your time. Thank you for listening. And I think at this time we're opening up for QA. I wouldn't let go 2 minutes over. All right, thanks. Bye.